It's actually wild. 9 out of 10 students are quietly bleeding crucial exam marks right at the very start of their computer science papers. They don't even realize it's happening. Today, we're jumping straight into the high-stakes reality of the IGCSE exams to figure out how a completely tiny, seemingly harmless error can just cascade into a total system failure.
So let's look at this specific challenge, converting 10 area 155 to binary. I mean, it looks simple enough, right? But an overwhelming majority of students completely fail this exact conversion. We're going to plunge straight into the raw data here to figure out why. What is the exact logic flaw that trips everyone up?
Well, it all comes down to the off by 1 fatal flaw. The most frequent mistake? Starting the positional value table at 0 instead of 1, or just completely miscalculating those powers of 2. Think about it. When your binary placeholders start at 0, then 1, 2, 4, instead of actually doubling properly, your digital values are doomed. The math just completely cascades into total failure from literally the very first bit.
Okay, so how do we actually fix this? Step 1, build that 8-bit grid perfectly. You work right to left, 1, 2, 4, doubling all the way up to 128. Step 2 is the subtraction test. Ask yourself, okay, is 155 greater than 128? Yes, it is. So pop a 1 in that column and subtract 128 from 155. Then step 3, the summation rule. You just repeat this test, moving right down the grid. Do that, and you'll reliably convert 155 into 1001111. Oh, and here is a golden exam strategy for you. Always, always show you're working. Even if your final bit is somehow off, having that beautifully drawn grid secures your method marks for sure. Section 1. Mastering Boolean logic and how abstract data makes decisions.
Now, possessing raw binary data is one thing, but how does the computer actually process that data to make a decision? Well, that brings us to the Boolean. A Boolean is basically a variable that can have one of 2 values, true or false. Think of it as the ultimate distillation of those ones and zeros we just talked about. This is literally the foundational building block for all the logic gates in digital circuitry. Every incredibly complex decision a computer makes, it ultimately boils right down to these simple true or false values. Let's compare the core logic of AND, OR, and NOT gates using 0 and 1 inputs. The AND gate is super strict. Both inputs, A and B, absolutely must be 1 to output a 1. The OR gate, much more flexible. If either input is 1, boom, you get a 1. And the NOT gate is the rebel. It just inverts the input signal entirely. Give it a 1, it spits out a 0. Give it a 0, you get a 1. To put that into perspective, let's apply these Boolean operators to a real-world scenario. Let's say your decision to do extra study. That equals true if you are behind at school, or if you are not behind at school and a friend asks to study. See what we did there? We just mapped algorithmic logic perfectly onto everyday human choices. It's a great reminder of how abstract programming just mirrors the exact same conditions we evaluate every single day. Moving on to Section 2, Inside the Silicone Brain, Mastering the Fetch-Execute Cycle. All right, so we've got the logic down. Now let's transition from the abstract into the physical hardware. Where do those true and false operations actually happen? Inside the CPU. The setup includes the control unit, which is basically the conductor of the system, managing the whole flow of instructions. Then you've got the arithmetic logic unit, or ALU, where the heavy lifting happens, the math calculations and logic comparisons. And surrounding all of that are the registers. These are ultra-fast internal storage spots, holding the data that is currently being processed. Now, there is a classic examiner trap here that you absolutely need to avoid. Let's clearly contrast 2 very specific registers. The program counter, or PC, holds the address of the next instruction. Contrast that with the accumulator, the ACC, which holds the results of the ALU's calculations. Think of it this way. The PC is about where we are going next, while the ACC is about what we literally just calculated. It is incredibly easy to mix these up when you're under pressure in an exam, so lock that difference in. And this whole setup puts the cycle into continuous motion, the classic 3-step loop: fetch, decode, execute. First, high-velocity data is fetched from the main memory, the RAM, right into those internal registers. Second, that instruction gets decoded inside the control unit to figure out, what action is actually required. And finally, we execute those commands, which usually means the ALU performs some kind of mathematical operation. And then it just loops.
Continuous, steady, blazing fast.
Section 3. Software Essentials. Orchestrating the hardware.
Here's the thing, though. All that complex, glowing silicon hardware, it is completely useless without a director to orchestrate it. At the base level, we have that deep background orchestrator, system software, which includes your operating system. It manages the hardware, gives you a stable platform. Then, floating at the top layer, we have application software. Those are the tools you actually use: word processors, web browsers, games. The OS is that absolutely essential foundation that makes running any of your apps possible in the first place. So, what exactly does the operating system do? Here is the rapid-fire checklist. It manages memory, handles interrupts, controls security, and facilitates multitasking across the CPU. Now, listen closely. The Cambridge Mark Scheme is actively looking for these specific technical nouns. If you want full credit, you need to use this exact phrasing. Commit these to memory. Section 4. Connecting the nodes, computer network fundamentals. Let's zoom out a bit. From the isolated workings of a single computer to how multiple machines share resources across a massive network. There's a fatal efficiency difference between two common pieces of hardware here. On one side, we have a hub. When a hub receives a data request, it is kind of dumb. It blindly broadcasts that data to every single computer on the network. It creates massive, unnecessary traffic. On the other side, we have a smart switch. This acts as a highly efficient, targeted distributor. Describing this efficiency difference clearly is a massive mark magnet on the exam. A hub broadcasts data to all nodes, which means low efficiency. But a switch? A switch sends data to specific MAC addresses. Highlighting that exact phrase, specific MAC addresses, proves to the examiner that you truly understand how a switch targets the intended recipient, which drastically reduces network congestion. Section 5. The Exam Mastery Strategy. Securing your grade. Okay, we have covered a massive amount of ground today, from binary and Boolean logic down to CPU registers, up through OS functions, and all the way out to network hardware. Bringing this all together requires a tangible battle plan. That's the 3-pass revision cycle. Pass 1, secure your definitions. Pass 2, rehearse your diagrams, like that CPU architecture. And Pass 3, which is absolutely crucial, avoid generic answers by always anchoring your response to the specific context of the scenario they give you in the exam. Let's walk through this 4-step mastery path, because this is how you upgrade a basic factual statement into a high-level, perfectly reasoned explanation. Step 1, diagnose the demand. Figure out what the question actually wants from you. Step 2, anchor to context, using the nouns from their scenario. Step 3 is the 4-prompt check. Just ask yourself, what is it? How does it work? Why is it used? And finally, check for completeness. Are you missing any steps? To wrap up this explainer, I want to leave you with a bit of a provocative thought. If your CPU executes a flawless logic loop, but the network hardware broadcasts the result to the wrong MAC address, where did your system actually fail? It's all connected, right? Understanding this deep system interdependency is the true key to mastering computer science. If this explainer helped make these complex concepts click for you, make sure to subscribe to us at acetheexams_IGCSE. Next time, we're taking these foundations and diving deep into the high-stakes world of cybersecurity. See you then.